Hello everyone. So today in this session we are here to discuss the concept of combinational circuits. Okay. So firstly we will see the concept of what is meant by a combinational circuit. So when you observe the word, you find here combination, right? You are finding here the word called as combination. So what does it mean? The circuit is purely depending on the combinations. So generally what we will have input combinations. Okay, generally we will have input combination with us. So this circuit indicates that the entire operation of the circuit will be depending on the input combinations. Clear? So the circuit which is purely functioning on the combinations. Okay, it is purely depending on the combinations. Now, so how can you state the definition? The circuit which depends, that means the output of the circuit depends only on the input combinations. In that scenario you call that circuit as a combinational circuit. Okay, the circuit at which the output depends only on the input combinations, okay, it is called as a combinational circuit. Okay, the circuit where the output is depending on the input combinations, it is called as combinational circuit. So this combinational circuit consists of input variables as well as logic gates and output variables. Okay, the combinational circuit consists of input variables, logic gates and output variables. Why these logic gates are there? Why? Because these gates accept the input signals and generate the output signals. That means internally in this circuit, internally we will have the logic gates, and these logic gates will accept input from here and process them and give output here. Okay, so if you see the block diagram here, you are having n number of input variables and these are given inside the circuit. So here processing will be started and then you will have m number of outputs. Okay, and the important point is the output of the circuit. Which circuit? Combinational circuit. The output of the combinational circuit depends only on the input combinations. This is the important point you need to remember. The output of the circuit depends only on the input combinations. So if you see the block diagram, we are having n number of input variables and m number of output variables. Okay, so remember that the circuit which output of it is depending only on the input combinations, that condition you call as a combinational circuit. Okay, inside the combinational circuit we have logic gates which accept the inputs and generates the outputs. So what is the function of logic gates present inside the circuit is these gates accept the signals from the inputs and generate the signals to the outputs. Clear? So this is the introduction of combinational circuit. Then we will see how to design the circuit, how to design the combinational circuit. So see here, the design procedure involves the following steps. We are having some steps. Okay, what is step number one? Step number one is you need to write your problem statement. Okay, that is step number one. What is problem statement? The statement which defines your requirement is called as your problem statement. Then what is your second one? By depending on the problem statement, you need to find out how many input variables you need and how many output variables you need. That means you need to determine the number of input and output variables required for you. That is second step. And what is third step? In the second step, we will fix some values. Right? We will fix, for example, I need 3 inputs and I need 2 outputs, or I need 4 inputs, I need 1 output. Like that, you will fix some values. So for these values, you need to name them. Okay, you should assign the letters or symbols. Suppose if you are having 3 inputs, name them like ABC. If you are having 1 output, name it as Y or F or X, whatever it may be. So whatever the count you are fixing in step number 2, for those inputs and outputs, you need to assign the symbols. You call it as a naming of the inputs and outputs. Next, this is the crucial step, very, very important step. Step number 4, that is framing of truth table. You should define the truth table which includes the requirement of the relationship between the inputs and outputs derived. Here you have derived inputs and outputs, right? So you need to form a truth table in which that table will define the required relationship between the inputs and outputs. Okay, so this is the truth table. And the next step is the simplified Boolean expression is obtained. How will you get? By using K-map. By using K-map, you reduce the expression into minimum number of terms so that uh, you need, so that you can easily design your circuit. Okay, so by having the simplification, you will get some minimized expression, right? So that expression you should draw the logic diagram at the end. Okay, these are the six basic steps you need to follow for designing of a digital circuit, which is called as a combinational circuit. Okay, so what is the step number 1? Problem statement. What is step number 2? Defining of input as well as output variables. What is step number 3? Naming of those inputs and variables. And what is step number 4? Deriving of truth table. Deriving of truth table. And what is here? Simplification. It is nothing but simplification. And what is last one? Logic diagram. Last one is drawing the logic diagram. So these are the basic 6 steps you need to follow for designing any digital circuit, right? So please remember these 6 steps, and while following the 6 steps, you should keep some points in your mind. Okay, you should keep some points in your mind, and by considering them, you should follow these steps. What are those? What are those? Let us see. These are the 4 minimum constraints you need to consider whenever you are designing a combinational circuit. What is the first one? You should have the minimum number of gates. Okay, that means the circuit what you are going to design should consist of a minimum number of gates. That is the first constraint. And second one is you should have minimum number of inputs to your gates. That is second one. And third one, you should have minimum propagation time for the signal through circuit. And the last one, you should have minimum number of interconnections. So in order to obtain these minimum conditions, the one and only thing is you should obtain an expression with a simplified version. Until unless your expression is simplified with the minimum number of terms, you cannot achieve these 4. Okay, please remember that. In step number 5, what you are doing there, you are finding K-map simplification and you are obtaining the minimum expression. So in that minimum expression, please see that the expression what you are going to write is the final expression, and still simplification is not possible. Then only you can achieve this one. Clear? Now let us see an example. So what is a given example here? Design a combinational circuit with accept 3 input variables that will produce output 1 when more than one input variables are 1. So what is the meaning here is they are asking to design a circuit in which the circuit output will be 1 when among these 3 input variables more than one input variable should be 1. In that condition only output will be 1. So as per the condition, what is the step number 1? Problem statement. Step number 1 is problem statement. So first you add, what is the problem statement? How will you write? 2, and let's copy the same question. 2, design, same, continue here. Design a combinational circuit, they're having this position, same. Copy the entire 3 input variables that will produce logic 1. Okay, the entire question is copied here. Just to add a word called as to before that. So it will be a problem statement. Why? Because the problem statement will reflects the requirement what is given for you. Okay, next. So step number 1 completed. So that is problem statement. What is step number 2? Finding of input and output variables. So in the question they clearly given 3 input variables. So your input variables will be 3. In the question they have directly given you your input values should be 3. Okay. Then how many output variables? Output variables will be only 1. Why? Because they said that the output will be 1 when this condition is satisfied. Suppose if this condition is not satisfied, then output will be 0. Satisfied means 1. So we are having only 2 conditions. 2 conditions means 1 literal is enough for us. So output is 1 literal. Next, naming of this. Third step is naming of this. So I take 3 inputs as A, comma B, comma C. With the help of 3 alphabets, I named inputs as A, comma B, comma C. And what is the output? Output is Y. Okay, I name A, comma B, comma C as inputs and Y as the output. So naming completed. Then what is the fourth step? Truth table. Very, very important step and a crucial step for the designing truth table. Okay, so let me clear the screen and I will generate the truth table. See here. So total I took 3 inputs A, B, C and single output Y. So I assigned 8 combinations. Why? Because for 3 inputs I will have 8 combinations 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1. Now I am having 8 combinations with me. And what is the condition given? More than one input variable or 1. See here, 2 ones are there. Here 2 ones are there. Here 2 ones are there. Here 3 ones are there. So in this combination, this combination, this combination, and this. These are the 4 combinations which satisfies this condition. What is the condition? Among these 3 inputs, more than one input should be 1. So that's why 2 inputs are 1, 3 inputs are 1. That condition I tick mark here. Okay, I kept a tick mark here. Okay, so these 4 conditions. So there only I should write 1. Okay, see here. For this combination, you should get 1. And for this combination, output should be 1. And for this combination, output is 1. And for this combination, output is 1. And rest of all will be 0. 0, 0, 0, 0. So like that, you should frame the table. Okay. After this table, you draw a K-map. Why? Because simplification. Same concept. Keep the ones wherever you have ones in the previous truth table and start grouping. Only we will have 3 pairs and the answer of this will be. So if you observe this expression, this is the final ultimate expression where simplification is further not possible. So I can say that it is the minimized finalized expression. Minimized final expression. So take this as your final answer. This is step number 5. And what is step number 6? For this particular statement or for this particular expression, you should draw the logic diagram. So take this as a question and draw the logic diagram. How will you draw? We are having 1, 2, 3 product terms. So take 3 AND gates. Product terms means AND gates. And what are the inputs given for these AND gates? First one is A, C. What is second one? B, C. So B, C. Okay, you should join them like this clearly. So draw carefully. Next here A and here B. And all these three should be given to which gate? OR gate. Why? Because these are summing with each other. So you draw one OR gate carefully and write here what is the expression given? Y, capital Y. So write here capital Y. So this is your circuit diagram. This is the final circuit diagram. Okay. Next. Okay. Now we will see the best example of the combination circuit is adder circuit. Okay. So how can you define adder? The adder is a circuit which performs the addition operation between the input combinations. Okay. Adder is a combinational circuit which performs the addition operation between input variables. Input variables. This adder is classified into two types. One is half adder. One is half adder, and second one is full adder. Second one is full adder. So let us see what is half adder and full adder. First we will see what is half adder, then we will see what is full adder. Okay. So what is half adder means? The combinational circuit that performs the addition between only two bits. Please remember this. Okay. If the addition is done between only two bits, it is called half adder. You will have only two inputs. Only two. So when you perform addition, you will get two outputs generally. What is sum and one is carry. That you know already. For any addition operation, you will have you will have only two outputs. You will have only two outputs. One is sum, one is carry. But here condition is inputs will be two. If the operation is performed, which operation? Addition operation. If the addition operation is performed between only the two bits, it is called as half adder. So this is the diagram. Okay. Next, we will see the truth table. See, two inputs A, B, sum and carry. So when you add 0 plus 0, you will get 0, 0. You will add 0 plus 1, you will get 1, 0. When you add 1, 0, you will get 1, 0. But in this case only, you will see carefully. When you add 1 plus 1, sum will be 0, carry will be 1. Why? Because it is a binary addition. Suppose if you take the same case in case of Boolean algebra, 1 plus 1 is equal to 1. Remember, in Boolean algebra, 1 plus 1 is equal to 1. And in binary addition, 1 plus 1 is equal to sum 0, carry 1. Next, as these two are the outputs, sum is output, carry is also output. So we should find two output expressions, one for sum and one for carry. So by using 4-cell K-map, you plot the given values and the carry you will get AB. Why? Because we are having only one here. So A is 1, B is 1. So AB. And for sum, you will have two independent variables. Why? Because no grouping is done here. Why? Because they are adjacent cells, not adjacent cells. So this answer is A bar B and this one is AB bar. Okay. If you see clearly, this is looking like A XOR B. It is the output expression for A XOR B. So the sum value can be written as A XOR B. So I written XOR gate, directly given inputs A, B, and the sum value is A XOR B. Sum is equal to A XOR B. And what is the carry value? AB. So I took an AND gate separately. I took AND gate like this. I attached the inputs A and B as it is, so that the carry will be AB. So the circuit diagram of half adder consists of one XOR gate. Okay, the circuit diagram or logic diagram of half adder consists of one XOR gate and one AND gate. Clear? Next, we will see what is full adder. Previously, half adder means only 2 bits. Full adder means more than 2 bits. It may be 3, 4, 5, anything. But generally, we will say 3 bits. But remember that more than 2 in the sense it is full adder. So here you will get two inputs like A comma B and one extra input as C in. What is C in? Input carry. What is input carry? Suppose if you're adding two ones like this. So when you add like this, 1 plus 1 you will get sum 0, carry 1, and you write that carry in the left column. This is called as your input carry. The carry generated is acting as the input. That's why it is called as input carry. Okay. The one carry what we got in this column is again shifted to here. That's why it is called as carry in the form of input. So it is input carry. Okay. Next. So the inputs will be A, B, and C in. And what is the outputs? Generally you will have one is sum and one is carry. So you can call the output carry. Okay. Either you can write here or here, no problem. Okay. That's your wish. There is no rule to write here. You can write here also, no problem. You can write here as C out. Okay. Output carry. What is output carry? The final carry which we got at the end of the result is called as the output carry. Okay. This is the block diagram. Okay. This is the block diagram. These three are your inputs A, B, and C in. Sum, C out are your output. Next, same truth table. We are having second. Okay. Yeah. We are having three input variables now. So that's why we take 8 combinations. Okay. So total you will have 8 combinations. And when you perform addition between these three inputs, that means A, B, and C in, you will get required sum values and required carry values, same as the previous. But be careful when writing the three ones. While adding three ones, you will get sum 1, carry 1. While adding two ones, you will get sum 0, carry 1. Very, very important. Two zeros are added, not only 2, 4, 6, 8, and even number of ones are added, sum 0, carry 1. When odd number of ones are added, that means 3 ones, 5 ones, 7 ones, like that. When odd number of ones are added, sum will be 1, carry will be 1. Okay. Next. Same, by using K-map, you will find the carry and the sum values. Okay. Here you observe carefully. In this K-map, you find the ones remaining alone, which cannot be grouped at all. These are your independent terms. So when you have a terms like this zigzag, the direct answer is nothing but XOR input of the given inputs. XOR operation between the given inputs. So your answer will be A XOR B XOR C in. Directly you can write. Just to remember, this is a shortcut for you. When you find ones like this, zigzag, all 4 independent terms, your answer will be XOR between the inputs. Suppose if you find the same scenario in the case of 4 variable K-map, then your answer will be A XOR B XOR C XOR D. Why? Because 4 inputs are there. Remember that if this is the condition, directly observe the inputs and put XOR operation between them, A XOR B XOR C in. Okay. And obviously here you will have one product term for this pair, one product term for this pair, and one product term for this. So total you will have 3 product terms. So draw the logic diagram. See what is the value of sum? Previously we have seen sum value A XOR B XOR C in. So I took one XOR gate, applied inputs as A, B, C in. So here I will get A XOR B XOR C in. And for product term, C out, what we have? 3 product terms. First product term, second product term, third product term, and all being added to each other. So it is an SOP equation diagram. Okay, this is the circuit diagram for full adder. Okay. So one important thing is how to design a full adder using 2 half adders. Very, very important diagram for 2 marks questions. So you first take one half adder. What is half adder? The combination of one XOR gate with AND gate. Combination of XOR gate with AND gate. It is called as half adder. Take the same half adder and connect to a second half adder. Then you will get that the connection will be like this. So it is nothing but your sum and C in is taken input here, and You need one more extra OR gate. Okay, two half adders, one OR gate will help you to find the or frame the full adder. Okay, please note down this diagram, very very important. With two half adders and one extra OR gate, you can design the full adder. Okay, next the same concept like subtractors. When you perform the subtraction operation between only two bits, it is half subtractor. Okay, only two bits, say A and B. But in case of subtraction, you will find difference and borrow as your outputs. There you find sum and carry, but here you find difference and borrow. Okay, see here 0 minus 0 is difference 0, borrow will be 0. 0 minus 1, very very important. 0 minus 1, when you perform, so 0 minus 1, generally what you will get answer as minus 1, right? So this one will be your difference, and this minus is nothing but the borrow value. Okay, so keep like this. Next, 1 minus 0 is 1, no borrow. 1 minus 1 is 0, no borrow. So only you should be careful in this condition. Okay, 0 minus 1 is nothing but minus 1 is the answer. So 1 will be the difference and minus will be the, okay, minus will be the borrow value. Okay, next, same scheme of simplification. This is the only single independent term that is the answer for A bar B. Okay, you will get A bar B as the answer for this, and you will get here same A XOR B. Okay, XOR gate. The small difference is in adder, half adder, we won't find this one. Okay, in half adder, you won't have this in inverter. In half subtractor, you will have inverter. That is the only difference. Rest of the diagram is same. Okay, if this inverter is absent, the same circuit represents your half adder. If inverter is present, the same circuit will act as your half subtractor. Okay, same full subtractor. There we are having carry in, C in, input carry, like that here input borrow. There we are having carry out, C out, like that here having borrow out. Same definition, same format. So frame the truth table. Okay, so subtract clearly. When you are having 0 minus 1, definitely you will have difference 1, borrow 1. Okay, borrow will be obtained only when you subtract 0 minus 1. Clear? See here 0 minus 1, that's why borrow is there. Here also 0 minus 1, that's why borrow is there. Next here 0 minus 1, but here 1 is there, so no problem. Last, see, 1 minus 1 is 0. 0 minus 1 again will have difference 1, borrow 1. So clearly observe and write the truth tables. Here also see here ones are existing independently, zigzag way. So your answer will be A XOR B XOR C. Okay, either you can draw like this, or you can simply write 4 individual terms separately, and you can do like this. See, 4 individual terms means 4 product terms, 4 AND gates, and you can make them as well like this, or else you can write A XOR B XOR C, no problem. That is also correct, no problem. Okay, and for borrow, B out means you are having 3 different pairs, so 3 different individual terms you will get, so 3 product terms and connected to one OR gate. So this is the diagram for difference. This is diagram for output borrow. Okay, clear? And now, and when you see this, the same concept what you have seen earlier is, by using 2 half adders, we framed one full adder. The same concept, by using 2 half subtractors, you should fill the one full subtractor. The same concept. There also we used 2 half adders, one OR gate. Likewise here also 2 half subtractors and one OR gate will give you your full subtractor concept. The small change is addition of inverters here and here. Okay, addition of inverter here, addition of inverter here. These inverters won't present in the half adders concept. Okay, so like this we need to frame the circuit. Next, we will see binary and parallel adder. What is parallel adder? The bits will be parallelly added here. See, the full adders has been connected parallelly sequentially, that the C out of first full adder is becoming as C in for second one. C out of second one will be taken as C in for third one. Like that, the interconnection is made, and then when these are operated, directly you are getting some values at your output, and each and every C out will become as C in for the next one. Okay, so this is called your parallel adder. Parallelly the addition will be done, and parallelly you will get outputs S0, S1, S2. Okay, so just to learn this circuit diagram. Okay, full adders will be in a sequence. Suppose if they ask you to write 4-bit, or else they ask with 4 or 3-bit or 2-bit binary adder, 3-bit binary adder. In the sense, suppose if they ask with the 4-bit binary, okay, 4-bit parallel adder. That means you should take 4 full adders. 1, 2, 3, 4. Suppose if they ask you to 3-bit parallel adder, means you should take 3 full adders. 2-bit parallel adder means 2 full adders. 7-bit parallel adder means 7 full adders. Okay, the diagram will represent the number of bits. Okay, and remember that the C out of first one will become as C in for second, and C out of second will become as C in for third. C out of third will become as C in for fourth, like that. Okay, C out will be becoming as C in. That is the concept between this interconnection between here. Okay, this is your adder circuit. Directly this A and this A1 and A2 and till AN. Likewise, this B0, B1, B2 till Bn. This will be added parallelly. Okay, and you will get outputs at a time S0, S1, S2 till Sn. Okay, it is a common diagram given. So please see that whenever the number of bits, suppose if it is n bit binary adder, n bit parallel adder, you will have n full adders. Okay, likewise, you are having subtractor also. What is the difference between subtractor? Addition means no inverters. Subtraction means one inverter will be there. See, inverter is given for the second input. Why? Because why? Already I said that subtraction, how the system will take, it will take into complementary addition. It means it converts into a plus of minus b. Already I said in the concept of binary subtraction, a minus b is our format, but system will take like a plus of minus b, which is called as complements. Like this, add inverter for b, same diagram, add inverter for b. That's it. The same diagram previous. Okay, if you see previous diagram, here no inverters are there, but here inverters are there. That's it. This diagram is same. Okay, see, as it, even though it is subtractor, internally we are making addition operation. That's why we will take full adders. Okay, even though it is subtractor, we converted the subtraction operation into a plus of minus b. That's why we are taking full adders here. Don't write here full subtractor. Okay, you should write full adder only. Why? Because subtraction operation is converted into complementary addition. Okay, so till here adders and subtractors are completed. We will meet in the next video with a new topic. Thank you and have a nice day.